Molecular clouds represent one of the most critical components in the cosmic process of star formation, serving as the birthplaces of stars throughout our galaxy and beyond. These vast, complex structures of gas and dust are the primary reservoirs of the cold molecular gas necessary for star formation to occur. The relationship between molecular clouds and the stars they produce is fundamental to understanding not only the life cycles of individual stars, but also the broader patterns of galactic evolution and structure. Molecular clouds serve as the essential link in the continuous cycle of matter in the universe, where gas condenses into stars, stars evolve and expel material, and this material eventually recycles into new generations of molecular clouds and stars. Molecular clouds are immense regions of interstellar space with sufficient density to allow the formation of molecules, particularly molecular hydrogen, H2. While the average density of the interstellar medium might be just 1 particle per cubic centimeter, molecular clouds can be tens to thousands of times denser. These clouds earn the nickname stellar nurseries when star formation actively occurs within them. The interstellar medium consists of various components, but it is within these molecular clouds that the conditions become favorable for gravitational collapse, leading to star birth. Understanding molecular clouds requires examining their structure, composition, and the physical processes that govern their evolution, all of which directly influence how stars form within them. The composition of molecular clouds primarily consists of molecular hydrogen, which makes up the vast majority of their mass. However, because molecular hydrogen is difficult to detect directly through infrared and radio observations, astronomers often use carbon monoxide, CO, as a tracer molecule to map these structures. Beyond these dominant components, molecular clouds contain a rich variety of other molecules and compounds, including methanol, ethanol, benzene rings, and complex structures known as polycyclic aromatic hydrocarbons. This chemical richness provides the building blocks not only for stars, but potentially for planetary systems, and even the precursors of biological molecules. Dust grains within these clouds play a crucial role by shielding the inner regions from ultraviolet radiation, allowing molecules to form and persist rather than being dissociated by energetic photons. The internal structure of molecular clouds is far from uniform, exhibiting a complex array of filaments, sheets, bubbles, and irregular clumps. This intricate substructure is crucial to the star formation process and develops due to the interplay of gravity, turbulence, and magnetic fields. Within these larger structures, astronomers identify two important substructures: clumps and cores. Clumps form the larger substructure of the cloud, averaging about 1 parsec in size, and are considered the precursors of star clusters, though not every clump will eventually form stars. Cores, being approximately 10 times smaller than clumps and possessing higher densities, are gravitationally bound and represent the sites where individual stars or small stellar systems will form through gravitational collapse. Filamentary structures have been identified as particularly important features in molecular clouds. These dense molecular filaments fragment into gravitationally bound cores, most of which will evolve into stars. Recent research suggests that these filamentary structures play a crucial role in determining the initial conditions for star formation and influence the final mass distribution of the resulting stars. The spacing of dense cores along these filaments, typically around 0.15 parsecs apart, appears comparable to the inner width of the filament itself, suggesting a regulated fragmentation process. This filamentary nature of molecular clouds has profound implications for how stars form and cluster together. Molecular clouds form and evolve through processes occurring on galactic scales. The formation of these clouds appears to result from large-scale compression of the diffuse interstellar medium, driven by various mechanisms including supernovae explosions, magnetorotational instability, or gravitational instability in galactic disks composed of stars and gas. These compressions generate turbulence that accelerates molecule production and shapes the observed morphology of the clouds. Among the proposed mechanisms for cloud formation, gravitational instability likely serves as the primary driver. Regions with higher gas concentrations exert greater gravitational force on neighboring areas, drawing in surrounding material and increasing density, which in turn enhances gravitational attraction in a self-reinforcing process. The life cycle of molecular clouds is relatively brief in astronomical terms, with most clouds existing for approximately 10–30 million years before being destroyed or undergoing major structural transformations. This limited lifespan can be inferred from the age range of young stars associated with these clouds and the absence of significant cloud material around older stars. Throughout their existence, molecular clouds exist in a dynamic state rather than a static one, with turbulence, gravitational forces, and feedback from forming stars constantly reshaping their structure and determining their fate. The continuous cycle of cloud formation and destruction completes when gas dispersed by stars eventually cools and is pulled into new clouds through gravitational instability. Star formation begins when the densest regions of a molecular cloud begin to collapse under their own gravity. This gravitational collapse fragments the region into smaller clumps, which continue to accumulate interstellar material and increase in density through gravitational contraction. As material falls inward, the temperature at the center rises until it reaches the point where hydrogen fusion can begin, marking the birth of a protostar. The entire process from initial cloud collapse to the formation of a star like our Sun takes approximately 1 million years. During this process, conservation of angular momentum causes the formation of a rotating disk around the protostar, from which planets and other orbiting bodies may eventually form using the leftover material from the star's birth. Within molecular clouds, star formation typically occurs in groups rather than in isolation, resulting in star clusters and associations. This clustered star formation is a consequence of the fragmentation and simultaneous collapse of multiple regions within the cloud. The first gravitational instabilities only set the seeds of star formation, while the final masses of stars are further influenced by accretion from the surrounding reservoir of gas. For high-mass star formation, competing models suggest different mechanisms. In the competitive accretion model, gas is funneled into the center of the gravitational potential, allowing some protostars to grow substantially larger than others. Molecular clouds play a central role in regulating star formation rates across galaxies. Giant molecular clouds, vast assemblages containing more than 10,000 times the Sun's mass and spanning 15 to 600 light-years in diameter, serve as the primary reservoirs of cold, star-forming molecular gas in the Milky Way and similar galaxies. The relationship between star formation and molecular gas follows certain patterns across galaxies, with a tight correlation between star formation rate surface density and molecular gas surface density. This relationship suggests that the star formation process, despite its complexity at smaller scales, exhibits self-regulation at galactic scales. Feedback from newly formed stars significantly impacts the star formation process and the molecular clouds themselves. Outflows from young stars play important roles in determining the efficiency of star formation. Once stars form within a molecular cloud, they begin to ionize portions of the surrounding cloud due to their heat, creating what astronomers call champagne flows of evaporating gas. This process, along with stellar winds, contributes significantly to cloud dispersal and typically begins when approximately 2% of the cloud's mass has been converted into stars. This feedback mechanism limits the overall efficiency of star formation in molecular clouds to relatively low values of approximately 1 to 10%. Molecular clouds represent the essential bridge between diffuse interstellar gas and the formation of stars. Their complex structure, chemical composition, and dynamic evolution directly determine the rate, efficiency, and characteristics of star formation throughout galaxies. The relatively short lifespans of molecular clouds, coupled with their low star formation efficiencies, indicate that star formation is a dynamic, self-regulated process rather than a steady-state one. Understanding the role of molecular clouds in star formation requires recognizing the multi-scale nature of the process, where cloud-scale evolution is sensitive to large-scale galactic conditions, while galactic evolution is in turn influenced by the cumulative effects of star formation and feedback occurring within individual clouds. As our observational techniques and theoretical models continue to improve, our understanding of these stellar nurseries will undoubtedly deepen, providing further insights into the cosmic origins of stars like our Sun.